For the sample problem regarding sensible heating process, this one is taken from one of our reference texts, this course, Ventilation of Agricultural Structures by Helixson and Walker. It says here that determine the heat required to raise 81 cubic meter of air at condition 10 degrees C for the dry bulb and 80% RH to 32 degrees C for the dry bulb. And also we are asked what is the final relative humidity, right? So from initial temperature 10 degrees to the final temperature of 32 degrees. Okay, so for the solution, so step 1 as always is to plot the states in the chart, okay, and obtain necessary data. Okay, so 10 degrees C dry bulb and 80%. Let's write it here. 10 degrees C dry bulb and 80% RH. That's initial point, and final point is 32 degrees C. Okay, so let's plot this. 10 and 80%. We have right here, that's the 10, and the 80% is, this is 80%, right? So that's the 80%. So our point is right here. So that's point 1. And then the final state is 32 degrees C. So 32 degrees C. So this is 30, 31, 32. So right here. Right, and for the moisture content, we have here the moisture content of around 0.006. Right. So 0.006, that's the moisture content. So we can write here 0.006 kilograms of water per kilograms of air. Okay, and what else? We have the temperature, we have the moisture, then the next one is we should have the energy. Okay, so next is the energy. Well, here's our enthalpy lines. So it's right here around 25. H1 is 25, say 25 kilojoules per kilogram dry air, and our state at state 2, you're here, and we need enthalpy lines as well. So this is around 0. Maybe 0. or 47. So H2 is equal to 47 kilojoules per kilogram dry air. So that's 47. Okay, what else? says here raise 81 cubic meter of air. So that's the initial. So we need the volumetric or the specific volume of air at point 1. And so for the specific volume, here it is. So that's approximately maybe 0.881. Maybe we can say 0.81, right? So this is 0.8, this is 0.85. So maybe you can say V1 is equal to 0.81 cubic meter per kilogram. Okay, so if that's the plot, then we can just write here C attached. Right? So C attached sheet. And for the data, we have the dry bulb, or I think we only need the H1, the H2, and the volumetric flow rate, as well as the given volume. Right, so this is 81 cubic meter. 81 cubic meter. For the specific volume, 0.81, 0.81 cubic meter per kilogram of dry air. And for H1 and H2, 25 and 47. This is 25 and 47 kilojoules per kilogram dry air, kilojoules per kilogram dry air. Okay, so now that we have the data required, then the next step is actually we can obtain the final RH. So the final RH can be obtained from the reading. Obtained from reading. Okay, so going back to our plot right here. So here's our final point, and you see here that here's the RH line. That's around 20%. And so 20% RH at 2 is equal to 20%. So at point 2, or state point 2. Okay, next one is how much heat is required. So calculating now the heat required. Okay, so calculating now the heat required. So recall that the equation is just simply Q is equal to M. That's the mass flow rate of the air times the delta H, or H2, or let's just write delta H. The change in the enthalpy, and of course we are referring to sensible heat. Okay, so the mass flow rate, this one is, the unit of this should be in kilograms per second, but we only have cubic meter, and that's the reason why we obtain this value of this specific volume, so that we can have kilograms later on. So this is the volume divided by the specific volume. Okay, so that's the equation, divided by the delta H, or H2 minus H1. So final minus the initial, and that's heat added, so therefore that's gonna be positive. So the volume is 81 cubic meter divided by 0.81 cubic meter per kilogram of dry air. So this is not a flow rate, this is only a volume, so no, it's not a flow rate. So we only will have a unit of kilograms only. Okay, so kilograms only. not kilograms per second. Okay, now for the H2, H2 is 47 minus 25, and the unit is kilojoules per kilogram dry air, and our remaining units would be kilojoules only. Alright, so if you do the analysis for the units, we only have what's left is the kilojoules. Okay, so now let's compute this. .81 divided by 0.81 times we have 47 minus 25. This is 2,200. So 2,200 kilojoules. Right, so that's the amount of heat required to raise the temperature of this given volume of air. Okay, so next is we'll talk about the sensible cooling process. Okay, next is sensible cooling process. So sensible cooling process. Alright, so similar to heating, but instead of increasing, it's about lowering the temperature, but lowering the dry bulb temperature. Okay, so how does it do that? So of course there must be an equipment. Instead of heating coils, then it will be, let's say, a cooling coil or something, maybe heat exchangers, right? So when the air passes right here, let's say a hot air passes right here, or an air with higher temperature, then it exits at a lower dry bulb temperature, but still maintaining the same moisture content. Okay, so in terms of the psychometric chart, so here it is, our chart. So instead of going to the right, it will be going to the left, right? So here's our state 1 and here's our state 2. And if this is our dry bulb 1 and here's our dry bulb 2, then there's a change in temperature. There's a delta T, but the temperature will at lower temperature. This is higher, D1. Let's just write DB1 is, or let's just write DB2 is lower than DB1, but the moisture content is the same. So that's sensible cooling. And again, whenever there's a change in the temperature or change in the moisture content, there must be some energy that's added, and we can obtain that by this. So H1, and this is H2, and that's going to be the sensible heat. Which is equal to the total heat in this process. And you would notice if we take final minus initial, what you get is a negative Q. So our working equation is a negative. It will be a negative Q. It just simply means that it's removed from the system. And take note that the dry bulb temperature of the air must be above the dew point temperature. So take note of that. This one should be, or the final dry bulb temperature should be above the dew point temperature, because if it is below the dew point temperature, then some of the water will condense, and therefore it's not going to be the same anymore for this. Right, so just take note of that. So now we'll do, for the energy balance, it's still the same. The mass balance is still the same, except for the signs. One is negative. So anyway, now we'll do a sample problem regarding this cooling process. Okay, so for the sample problem of this sensible cooling process, this one is still taken from the same textbook. It says here, determine the amount of heat removed from 30 cubic meter of air initially at 40 degrees C dry bulb and 30% RH, which is cooled to 25 degrees C dry bulb without changing the moisture content. Okay, so first step, as always, is to plot. So plot and obtain necessary data. Obtain necessary data. Okay, so it says here 40 degrees C dry bulb and 30% RH. 30% RH, 40 degrees C dry bulb, and that's for state 1. And for state 2, we have what's this? 25 degrees C. So 25 degrees C dry bulb. Okay, so first is to plot the dry bulb. We have 40. So here's our 40 degrees. Right. So 40 degrees and 30% RH. So here's the 30%. And therefore our initial condition is right here. So that's 0.1. Okay, and it's cooled down to 25 degrees C. So 25 degrees C is somewhere here. Right. And since this is a sensible cooling process, then therefore the humidity or the moisture content is constant. Right. Maybe right here. Okay, so the humidity is 0.014. Maybe you can write 0.0138. So humidity is equal to 0.0138. Okay, what else? We also need, so humidity is 0.0138 kilograms of water per kilogram of dry air. And what else do we need? We also need the enthalpy. So for the enthalpy, so we trace these lines. Or we'll just draw another line. So what's this? H1 is 76. So H1 is 76 kilojoules per kilogram, and this one is, let's say, 60 kilojoules per kilograms. Okay, so therefore so H1, of course you have to write the H1 and H2. H1 is 76 kilojoules per kilogram, and this one is 60 kilojoules per kilogram. And we also have the volume of the air, which is 30 cubic meter. So 30 cubic meter. So solving now. So solve now for the mass of air. This time this is not a flow rate because this is just cubic meter. Therefore, um, mass of air is equal to the volume all over right. So we need also the specific volume. So for the specific volume at point 1, so let's just say 0.91. So volume is 0.91 cubic meter per kilogram of dry air. Right, so therefore 0.91, and this one is 30. So the mass of air is 30 divided by 0.91. This is 32, or let's just say 33. 33 kilograms of air. And now we can solve for the heat removed. So we should just simply Q is equal to MA times delta H, the change. And take note, this is heat removed, and it's gonna be subtraction or negative, but the magnitude is the same. So 33 kilograms of air times the delta H, this is 76 minus 60 kilojoules per kilogram of air. So what's left is kilojoules. And now let's do this. 33 times 76 minus 60, let's just write 16. This is 528. So 528 kilojoules. So next process that we'll discuss is the cooling and the humidification process. Dehumidification process. Right, so basically, this cooling and dehumidifying process is a process whereby both the dry bulb temperature and the humidity ratio are lowered down. So cooling meaning we lower the dry bulb, and this one, dehumidification, meaning also lower the humidity ratio. Okay, so this happens when, or let's write it here, lowering the dry bulb and also lowering the humidity ratio. Okay, so this can happen when, for example, we have let's say an equipment, and we have a cooling coils as well, except that this time the temperature of the cooling coil is below the dew point temperature of the air, right? So let's say here's our air with high temperature, and then it exits at lower temperature, but because the temperature of this cooling coil is, or the final point is below the dew point temperature of this entering air, then therefore some of the moisture in the air will start to condense. Will actually condense, right? So if it will condense, then that means that some of the moisture will leave the airstream, right? So we have moisture leaving the airstream right here. So moisture condense, or condensed moisture, right? Condensed moisture leaving the airstream. Okay, so that's one way, and another way is, let's say we have an air washer. So it's an equipment, and let's say we have here some air washer. So it sprays it sprays water, cold water, into the airstream. Right, so it sprays cold water into the airstream, and some of the some of the water in the airstream will also condense. Right. Okay, so of course, if this is a system or an equipment, then there must be some, let's say, a sump wherein the water is recycled back to the distributor or the header pipe right here. Right, so it must be recycled. Right, so it goes here and then goes back up again through a pump. Okay, and this will be a something like a cooling chamber. That's right, cooling chamber. So that because when the air passes through this water curtain, then the energy of that hot air is transferred into the water curtain, and thereby increasing the temperature of the water curtain. So we need to bring this water temperature back to its original intention, so that we can do the cooling and dehumidification process. Okay, so now in terms of the psychometric chart, so cooling and dehumidification process is, let's say here's our state 1, and this will be our state 2. Right, so that's the cooling and humidification process. So if this is state 1, then here's our dry bulb temperature 1, and this will be our dry bulb temperature 2, and this will be our humidity ratio for state 1, and here's our humidity ratio at state 2. Right, so recall that this is a temperature difference, and this one is a humidity difference. Moisture difference. Okay, so in terms of energy, as I have always said, that whenever there's a change in the temperature or the change in the humidity, there must be some energy that's added or subtracted into the system or into the airstream. So since we have this change in the moisture content, then that means we have the latent heat. Right, so right here's our sensible heat, and here's our latent heat, and the total heat in order to arrive from point 1 to point 2, that's going to be the sum of the sensible heat plus the latent heat. Right, so of course in this point, this is H1, this is H2, but we have right here something like an intersection point between the vertical and the horizontal. So let's just label this. I mean, since it's a point, then it has a value for the enthalpy. So let's just write hx. Okay, another one is if we draw this schematic diagram for the equipment. Okay, so one way is, let's say we have here something, a coil or a refrigerant or something. So here's our airstream, hot air. Right, so here's our airstream. So it passes through this coil or through this equipment, and then exits at a lower temperature and lower humidity ratio. So if we consider this, or if we set up our system boundary right here, then what are the energy that enters the system, or what are the energies that leaves the system? So first one is the energy from the airstream. That's we have a mass of air or mass flow rate if it is per unit time. Then in depth mass, there's also the internal energy. I mean the enthalpy, and we also have this humidity ratio. Okay, so because this is a cooling equipment, then the heat will be going out the system. So that's our Q, and there will be some of the water that leaves the system, right? So the mass that leaves the system is not the air but the water. So we have mass of water, and of course that's going to be the enthalpy of the water. Take note, mass of water and enthalpy of water that condensed from the airstream. And right here we have mass of air, or if it's a mass flow rate, then we have an enthalpy at state 2 and also the moisture content at state 2.